too bad.
Okay, let's get started. We have a small class today. I was kind of expecting that since it's today we are going to talk about, we're going to review kind of the control stuff we've gone through, make sure everyone's clear on it. That's a great time to ask questions if you're not tracking like how we're setting up the control and why we're talking about certain things. We're going to discuss a little bit about frequency response and filtering today. Homework 5 will be posted today. I sent an announcement out. There's really only time for one more homework, I think. So in order to test all the content, I'll post the homework today, which will include today's content. There is, after the break, there is 4 lectures and 2 labs. The last class, we'll do a competition, probably in the Ford Atrium. So that's not going to be a class. So there's really 3 lectures and 2 labs. At least one of those lectures, probably 2 of those lectures will be content. Then you'll have about a lecture and 2 labs to just kind of work on your ballbot and get it to the place that you want it to be. The competition on the last day of class, that's going to be something like a balance competition and a steering competition. We're going to figure out exactly how we want to do that. Maybe like time, how long everyone's ballbots can balance, and so use the last one standing. You might put them all on a rug and basically perturb the rug and give it disturbances and then see. So we're going to figure out some way to do that, but that's the game. Hopefully we get our steering controller working well, in which case that would be the first lecture that you hear after the break. Then that's all we're going to learn. It's basically this, filtering, and putting it all together in your steering controller, and that's it. Yeah, 3 lectures, 2 labs, and a competition. Got your midterms back. The average wasn't terrible. It was 68%. So that's not bad. I don't know the standard deviation off the top of my head. I don't know if you guys know it. But my guess is it's about 10% or so. Maybe a little more, maybe 15. So there's a pretty big distribution. But it was not my averages are usually a little higher than 68, but that's within the realm of normal. I don't feel like you guys were way off base. I don't feel like the exam was way off base. So I'm happy with the 68% in a way. Yeah.
Will the solutions be posted to the exam?
I think so, yeah. I think I will post them. You want to see them?
Yeah.
Okay. Don't try to not distribute them, because there aren't a lot of materials for this class. So it'd be nice to try to be able to reuse some of it. But yeah, we can post the solutions. Yeah. Anything else? No, I think that's about it. Okay. So this is kind of where we are. We're talking about control, implementing it on your robot. This helped us understand what are the major tasks of control. In this style of control, we have a loop running. That loop is collecting data, it's analyzing that data, making sense of it, and then it's taking that data, creating a set of actuation commands and sending those, and then saving data. It just does that every loop. This is one strategy of building robots and controlling them, is to do this. Everything runs in this loop, and then you kind of operate on a loop by loop type function. Kind of went through the different steps here. I'm just going to go through these real fast since you've seen these before. But this was like our reading in the data. We've kind of done that for you, so that's easy. Actuation commands, we do some control. So we're using the data we acquire from the ballbot, lean angle, the information from the motor encoders. We're going to interpret that data, create a set of motor commands, send those out. This was we were talking about implementation of the integral term and how saturation can cause nonlinearity and performance issues. One thing I noticed kind of during last week's lab was a lot of people kind of basically went straight to implementing anti-windup and saturation in there. They added an integral term to their controller and their balance bot, and then they started focusing on trying to keep it from winding up without actually looking at the controller efforts. So it was almost like people sort of assumed, oh, if I have PID, I have to worry about this. And that's not the case. And in fact, my guess is you probably don't really have to worry about wind up in this case because the integral term doesn't end up being a huge aspect of the control. So what really the game is, tune your controller, assess what's happening with its performance. So look at the performance, record it, plot it, get an understanding of how the system is responding and whether it's doing what you want it to do. Look at your controller efforts, see whether controller effort from P, I, and D kind of look even or whether they make sense or is one term dominating. That's the information that would cause you to add an anti-wind-up term, not just that you're using PID. You want to see something before you use this tool. Does that make sense? Okay. This was kind of like why saturation exists. It exists because PWMs can only go to 100%. So once our gas pedal is floored, that's all we have. And this was kind of the issue of like wind up. The saturation occurs. So the controller would think that it's trying to send this kind of effort, but it can't. It's already at a maximum PWM lead cycle, so it gets truncated. It actually sends this effort, which makes the system's performance not do what it's supposed to do. You end up with a delayed response, which is something sometimes called kind of wind-up induced lag. Does that make sense? So if you were trying to implement this, you would be watching your controller efforts. That's why we did plotting. That's why we're calculating these controller efforts separately. We would watch our integral effort and look to see if it begins to dominate. And if it begins to dominate, how long does it take to remove that? That's kind of the issue, that the integral term would cause a bunch of error that then has to be removed. Okay, does this make sense? This is stuff I think you guys know reasonably well. This is about implementing the derivative side. We talked about the 2-point finite difference implementation of derivative. Very straightforward. The only problem is it's very susceptible to noise. Since we're doing a 2-point derivative calculation, it can get really noisy. In addition to the amplitude of a signal's derivative will be much higher. So it can be problematic. There are more intelligent ways to take derivatives. Anybody know? Anybody know of any? One potential option, this is what I use, would be you can keep the last, say, 5 data points instead of just the last one. So you keep a small amount of the last data, then fit a second-order polynomial to that data, and that can be solved in closed form. So you can get those coefficients easily. Then you can numerically differentiate that polynomial. And so that's less susceptible to noise because it's not using just the 2 points, the 2 most recent points. It kind of uses a collection of data points and fits to that set of data points. It's a little cleaner, but I don't have the, that's actually what DDT does. It's exactly what DDT does. Yeah.
Why the second order?
What?
Why are you using like a second order when you're fitting like?
Oh, why fit it with a second order?
Yeah.
It doesn't really matter. It's usually that if it's 5 points, you're not gonna be able to fit a high order model to it. A second order model has a cleanly take its derivative easily and set time equal to now. Solve. So it's just I think it's a good balance of like how many data points it needs and the fidelity of the derivative it provides. Okay, so yeah, this is the most common, but you can use more intelligent methods. I would probably use this for now. We talked about our signals being noisy. Our signals are actually pretty clean, but even though they're clean, they still have noise. Like noise if you take derivatives, noise is an issue, even if you have clean signals. This was our like overarching controller architecture. You've seen this a couple times now, but this is our balance controller. We built that. You guys saw how to do that. You tuned it, and now we're talking about adding a steering controller, which could superimpose on the balance controller. And this is just one way to do it. What's another way to do it? A different sort of architecture than this. It's come up a few times. A lot of you guys have thought of it. It's very similar to what's shown here, but I would represent it differently. If I said, let's say like you were not in this class, and I said, I want you to build a steering controller from your balance controller, what would you do? A lot of you talked about this already. I talked about it in lab. Modify the lean angle. So another option is to modify the lean angle. If we modify the lean angle, then that's the same if we lean it, that's putting a net torque on it in order for it to lean. So we could, for example, restructure this such that the lean angle is what's controlled instead of just applying torques from the controller. So anyways, there are lots of options for this architecture. This is one that we started talking about. We might actually end up doing something even different than this. Any questions on what that's saying? What is that like? Does everyone look at that diagram and feel like they track exactly why that's on the screen? Good. Okay, I'm gonna skip that one and go to the two-plane version. This was our PID controller. Actually, I'm gonna go to the controller one. So this is our controller architecture we have set up so far. We have our two-planar PID loops, our controller that does z-axis rotation. All of these things, what we really want is this t, x, y, z vector. That's kind of where our controller efforts are coming from, which we then can convert to the motor torques 1, 2, and 3, send those out, read how it changed the ballbot's position or pose, and keep going. Are there any questions on this? Everyone feel like they know exactly like what that's saying? That's controller diagram. Good. Like I'm imagining that if you understand this diagram, you could essentially change all of this stuff relatively easily. So if I said, I want you to make it a different controller, or I want you to control maybe not lean angle, I want you to control something else. Like with this, do you feel like with this, understanding this architecture, you could now control this ballbot by putting things together in any way that you thought of? Okay, good, that's what I want. I want you guys to be able to look at this and say, okay, I could do this, or I could do a different version of this. A lot of these things we're solving in this class have kind of multiple ways to do it. All right. This was just about sending actuator commands. It's not too bad. And then we kind of talked at the very end of the file, we gotta save our data so we can look at it later. But then we also have to transition these variables that come up as variables from 1 or 2 iterations ago. So we might say error x previous equals error x. It could say error x previous 2 equals error x previous. Like you could just stack all of it. At the end, you would just shift them all. So then the next loop iteration, they're all updated and ready. Does that make sense? Hopefully that's clear, yeah, good. Okay, now like today's topic, filtering. Anybody recognize this, or anybody know what this is? It's an analog filter. It's an RLC filter. Okay. So this lecture is meant to give you kind of an understanding of filtering, both what is it, kind of a little bit about how it works, and implementing it in MATLAB. Next lecture, we would do Python and then do the control side. One other thing is I won't be here next week, except for Thursday. So Tuesday, Eve will teach. Wednesday, Eve and Seth will run lab. I'll be back on Thursday. Okay. All right, filtering is a ubiquitous tool used in robotics and engineering. Usually a critical step with kind of any like real world data. If you're using data from the real world, you're almost for certain filtering. We use filters generally, like a common way to think about them is we use them to remove noise. You know what I say noise is unwanted corruption in your signal. Who can tell me like some places noise comes from? Why might we filter? Yeah.
Like 60 hertz noise from just ambient monitors and things you can.
Yeah, it's actually really common to get 60 hertz noise. So that's, we have oscillating electrical fields in the walls. Those oscillating electric fields can induce oscillating fields in your sensor and your data. So it's really common to have to filter out 60 hertz noise. Another one would be, what about like maybe sensor noise? So maybe our sensor is bad, or it's giving us noisy values, or we don't have a high quality sensor. Sound familiar? Also corrupted or uncertain data. And then essentially there's infinite reasons. Okay, filtering is passing a signal or an image, which would be maybe a type of signal, 1D or multiple dimensions signal through a dynamic system. So just like many of the things we've talked about in this class, filtering is going to have an input. It's going to go through, we're going to process this input through this dynamic system. It's going to give us an output. And that output is going to be a transformed version of our input. And it's going to change. So filtering changes the signal, transforms it, often, but not always. Smoothing over time. So this is an example of just a random signal I made. That's a 10 hertz signal. So the blue signal is a signal that I created that contains frequency content up to 10 hertz. We're going to talk about what that means. The red signal is that signal filtered, and it's filtered to remove the signal content after 3 hertz. So it looks smoother, it looks delayed, its amplitude is decreasing. So let's talk about why it looks like that. Okay. Let's begin by thinking about the time series data can be represented as a combination of frequencies. Do you agree that if I have any time series signal, I can think about that time series signal in terms of data, in terms of time, over time, just looking at the signal, but I can also think about it in terms of the frequency content in that signal. We can obtain this information by using a tool known as the Fourier transform. In the Fourier transform, the output, capital F, is our transformed signal. F of t is our original time domain signal. And e to the minus j omega t is a complex exponential. What does it encode, e to the minus j omega t? Anybody know? Say it again.
Sorry, I didn't understand the question.
What does it encode? What is it? E to the negative j omega t. Have you ever seen that?
A sinusoid?
The circle. Yeah, so that's really like encoding a frequency content. So that comes from Euler's law? Something. But anyways, this equation, we're going to take our time signal, we're going to multiply it by a complex exponential function, and we're going to integrate it from negative infinity to infinity. So you're not going to have to actually do that, but this is what's the background of how this transform works. So they can be transformed by this equation describing the frequency, content, and phase information. So we're going to talk about what is this actually telling you? It is a signal, a transformed version of our time domain signal, and this signal now is complex. So it's a complex number, and it's a function of frequency. Why do we use complex numbers? Like when you see complex numbers in engineering like this, that should like trigger something. What is the point of it? Why is this a complex number? So mathematicians made a choice to like encode it this way. What are they encoding? This I think you know, so I want to wait. So when Whenever you're working with a complex number, what are you doing? Like what class is it? What are you thinking about or analyzing? Differential equations? Probably. It should tell you that it's conveying two pieces of information, magnitude and phase. So it means for one point on our x-axis, for one frequency, we have two pieces of information, magnitude and phase. Because we have two pieces of information, we choose to represent that as a complex number, which has or defines magnitude and phase. Complex signal describes magnitude and phase, and sounds or sound signals or audio signals are like a tool we can use. Let's talk about things in terms of audio signals. That will help us. If you can hear it or think about it in terms of the audio world, I think it all maps into the signal world. I think it'll be great. You guys would agree sounds are composed of multiple frequencies. When you're hearing something, you're hearing the combination of many frequencies at once, and that gives it a particular sound. So we can view information, a signal, in both the time and frequency domain. I want to talk about that. I want you to really understand this picture. So consider three people whistling into a microphone. So you can imagine, what is that, if I were to record that with a microphone, what would it look like? It would look like this, or this. Or this. It would be a sine wave at the frequency that you're hearing. Okay, so if three people did it, we'd get three sine waves on the output. Maybe these three. So each one of these is a different frequency. It would sound a little bit different. And they might be shifted in time. We'll come back to that. If we sum them all up, it's going to look something like this. This is in time. So now we're looking at the sum of three sine waves. If we look at it in the frequency domain, we can look at it sort of this axis, look at it this direction. What it's going to show us is that there's a frequency here and this frequency, a frequency here, and a frequency here. We can also use the y-axis value to get an understanding of the amplitude of that signal. So signals in time can be thought of or represented in the time domain like normal, like it's intuitive, but also in the frequency domain. Does it make sense? Would it make sense to analyze a signal of zero length, of like zero duration in this way? Like how much frequency content is in like a sound with no length? The frequency content requires there to be some length that's considered, some duration. And if you do this analysis, it will return to you the frequencies in that duration. So if you did it for an entire song, it's going to tell you the entire song's frequency content. If you just did it for 1 second, it's going to tell you that 1 second worth of frequency content. Does that make sense? Okay. Does everyone fully understand this schematic? It is critical. I'm going to say it's comprised of single frequencies plus noise. So what if we talked about filtering in the frequency domain? What if we talked about it in something like this? That's where we're going. So we're gonna stop talking about things looking at it this way. We're going to start talking about things looking at it this way. Does everybody understand what that means? Okay. All right. This is just like a quick review or talking about the audio part. The way we implement filters and looking at frequency content is using the fast Fourier transform algorithm. So this is a specific technical approach to computing the Fourier transform of a signal, and it's efficient from a computational perspective. So you'll see the concept of words FFT come up. The Fourier transform lets us selectively, remove frequencies from data. So a music equalizer is a bunch of filters. You can imagine it might look something like this. And what's on the back end of this is it's taking your sound, your music, whatever is going through this, it's running it through a bunch of parallel filters. So each one of these would be a filter, and each one of those has a particular set of frequencies that it's either going to remove or let pass through. Really, it's going to, what would these filters do? Would they remove or let something pass through? Well, like what's happening? So we have our filters, they have the different bass, mid-range, treble. So we're going to adjust those. So here's our different filters to adjust our sound. We're going to take the outputs of those and sum them, and now we have a filtered version. So now someone tell me, like, what is one of those filters doing? Like, what's going on in there? Yeah.
Are they kind of just amplifying or attenuating the signal, depending on where the slide bar is set?
So that's true. So this is going to amplify or attenuate that slider. But what I'm trying to get at right this second is that there's a bunch of frequency kind of bins. And each one of those is going to remove everything but that frequency bin. So if you crank them all up, it's going to let all of it through. So when it reassembles, it would just reassemble the same thing. But if you crank them down, you're going to see like, so each one of those filters would look, if we looked at it in the frequency domain, in terms of what is it removing, it would look something like this. And then the next one would look something like this. So each one would have kind of a band of frequencies that are less pass through, and it removes everything else. Agreed? Make sense? Yeah? Make sense? Okay. Okay. So frequencies, this should say filters, are characterized by what frequencies are allowed through. There are many different types of filters. So you may have heard about them or seen different implementations of them. What they are doing is really defining exactly how these signals are passed through or removed. So there are many types of filters that differ in the specific frequencies they attenuate and how exactly that attenuation is defined. They can be run offline, so that means you record data, then you filter it after the fact, or they can be run online in real time, so you're recording data sample by sample and filtering it as you go. Or in real time. Let's think about some data from an actual robot. So this is data that I recorded from it. This is me walking on this prosthesis. So we're looking at somebody walking on data. We're looking at IMU data, vertical axis acceleration. When you look at this signal, what do you notice in terms of its frequency content?
Big range of frequencies.
What?
There's a pretty big range of
There's a
frequencies.
range of frequencies. How can you tell that?
Like pretty slow, periodic, where you're stepping, and there's also really fast, like maybe it's noise or something else.
Yeah, so each one of these is a step. And we see some periodic signal that's relatively low frequency, and we see some really high frequency information, contact, which looks like those impulses. So this is an impact event. This is sharp or jagged looking, but also has low frequency information. So I would kind of want you to be able to look at a signal and gather some general information about what's in it. There's some frequency content in the signal. It has some lower frequency content, and it has some higher frequency content. We're getting that by looking at the signal and kind of looking at how fast things are changing, whether there's periodicity at low time scales or high time scales, and things that are sharp, like these pulses like this, extremely high frequency. So now let's say we want to filter out those high frequency components. It looks something like this. So we're talking about a type of filter that's low pass, so we want to let the low frequencies pass through. And we want to attenuate the higher frequency impact events, for example. Maybe we want to do that. It's going to cause a slight delay, and it's going to seriously affect those oscillations in kind of high frequency parts. This is the same data in blue that we just saw. I filtered it at 3 Hertz in red. And now what we're looking at is its frequency content. So this is the output of the fast Fourier transform. Somebody talk me through red and blue. We're looking at the frequency content of red and blue. Yeah.
So the blue is the original signal with a lot of higher frequencies, but since we're trying to, it's a low pass filter, we're trying to filter out all those higher frequencies. So the red filtered data has very few or even almost 0 high frequencies and a lot more low frequencies.
Yeah, so it has sort of the same, it would have basically the same low frequency information, but if the filter cutoff, which we'll talk more about in a minute, is about 3 Hertz, kind of after 3 Hertz, we're losing all that information. So then when we look at how did that actually, what did this information that got removed look like? It looked like these jagged high frequency components. So this is showing us in the frequency domain what's different about this in the time domain. And you can almost always look at your signal in the time domain, put it in the frequency domain, and determine what frequencies are in it, which is helpful. Yeah.
What does a decibel specifically mean in this context? Like, is it converted from the acceleration?
Yeah. So this would be converted into decibels, which is just a conversion to talk about frequency domain concepts. I kind of want to I don't think the y-axis of this is a super important concept, and it is kind of tricky, so I'm going to skip it. So the Fourier transform back and forth. So you can transform something from the frequency world back into the time domain by the inverse Fourier transform, or from the time domain into the frequency domain using the Fourier transform. So here's our 3 Hertz removal. And then this is the removed parts of blue. What happens? So this signal has a value at 0 Hertz. What does that mean again?
DC offset.
It has a non-zero mean. Yeah. So let's say you are looking at a signal that had a really high DC value, oscillating not around 0, but around 20 million. Then when you did this, if you did this Fourier transform, you get a giant spike at 0 Hertz, which would make everything else look like nothing. It would just dominate that plot. But yeah, so sometimes if there's 0 Hertz, it can throw it off. You can just remove that by doing minus the mean. You could just analyze the system without the mean in it, and it'll remove that. Okay. Let's talk about how we compute the output of a filter kind of very, very basically. We can think about a filter as multiplying our signal by a function. In the frequency domain. Okay, that's how I want you to think about filtering. I want you to think about it as though we take our signal in time, we're gonna convert it into the frequency domain, so it's gonna look like that plot we just showed. Then we're gonna multiply that signal, the frequency domain signal, by another signal. Okay? What could these functions look like? Let's say it looks like this. This is our function in the frequency domain. We're going to take our function, our signal, convert it into the frequency domain, and then multiply it by this. What would that do? Nothing. It's multiplying all the frequencies by 1, so they're all the same. So this filter does nothing. What does this filter do? Yeah, this would apply a gain. So it's gonna take the signal, amplify it. So what I kind of want you to think about is we're taking our signal, turning it into the frequency domain, and then multiplying it by this red line. And the shape of this red line is what filtering is all about. So the left would do nothing. Then the right would amplify by 2x. And filtering is about specifying the exact shape of the multiplying function. Which is the red line in this context. There are 3 types of filters. Low pass, band pass, high pass. What do you guys think those do? What is low pass? What does a low pass filter do? Yeah. It does. It lets lower frequencies pass through. How about band pass? What happens there? Yeah. There's a specific frequency band that can pass through. High pass. Let's go with high frequencies pass through. Nice. Okay, great. So let's look at these functions, these multiplying functions. And I'm going to say they maybe look something like this. We have our low pass filter. So this is our amplitude and our frequency axis. So we're going to take our signal in the frequency domain and multiply it by this, which is going to let all the frequencies on this side of this get multiplied by 1, they pass right through. All the frequencies on this side get multiplied by a low value, they get removed. Same thing with band pass, same thing with high pass. Filters are typically defined by something we're going to call a cutoff frequency, which is the point at which they begin to change shape. The cutoff frequency defines what frequencies can pass through. Filters can be used to also apply a gain at the same time. That sort of comes for free. It just depends on what this intersection of the y-axis is. So filters often kind of do apply a gain at the same time. And remember, if the frequency domain is complex, having both magnitude and phase. What does phase describe? So talk to me about phase. I haven't actually shown phase. Phase is a little harder to wrap around. Like if you really try to dig into it, I think it's harder. So I'm trying to see if we can just keep it at kind of an intuitive level. What is phase telling you? Yeah.
At what point in the sinusoid the signal starts?
It is telling you that. That's true. I think a more intuitive definition of it would be it describes the delay that frequency will receive from being passed through that filter. So what delays would you expect these guys to have? The frequencies that are getting passed through, do we want them to be delayed? No. So the phase delay for these would be very close to 0. But what about these guys as they start to lose the ability to let it go through? Is there a phase delay? The phase delay starts to increase as this starts to attenuate. So not only do frequencies begin to be removed, their amplitude starts to decrease, they also start to get later and later. I think we want to kind of leave phase kind of around like that. Phase describes how frequencies begin to lag. The phase shift of 360 degrees is 1 cycle. So when we talk about phase shifts, we talk about it in terms of degrees, and the degrees are the degrees to make your frequency to make 1 period. So what I want to do now is kind of show you an example and kind of let you guys play with that. So first, just kind of watch on my screen and then we'll switch. Okay, now we're gonna look at some data. I have an M file, it's gonna import that data, process it, and we can look at its frequency information and filter it. And then I'm gonna show you how it works, and I want you guys to play with it. So what this is doing, it's gonna load in some of that data of walking on that prosthesis. This is gonna do the same kind of structure as when we used MATLAB to analyze our ballbot data. So I've created all the data that it's stored a bunch of interesting data, if you wanna see it. And then here, so here's where it's going to filter and compute the frequency content. So the cutoff variable here, you can change that. It's going to change the cutoff of a low-pass filter. If you change data to be filtered to another variable, it's just going to show you, it's going to perform this analysis on one of the other variables. There's all sorts of these variables, they all have different frequency content. So then what this is doing, you're gonna need this function. This is doing the FFT. So I have a function. There's a MATLAB FFT with lowercase f's that came out more recently, and then I made FFT, which just capital F's FFT, which just computes the single-sided amplitude spectrum. So it just does the FFT for you, and then saves the data. But if you use the FFT with FFT lowercase, it's going to give you an error. So that's going to plot. So let's look. So what I want to do is have you mess around with this. So plot different signals, change the cutoff frequencies, look at the frequency content, look at how the frequency content changes, and then I'm going to tell you a little more about actually executing the filter, creating the filter in software. So this is that same data. It's actually a little bit of a different segment of data, I think, but it's showing that same file filtered and then the FFT. So these data are now on Canvas. There's an M file and a data file. Go into Canvas, download that M file. Read it. There's not a lot there. It's mostly plotting, but look at how filtering is done. Look at how the data looks. Look at the FFT. Kind of build some knowledge around what signals look like when they're filtered. I'll add FFT to Canvas. Who's able to run that file? Nobody run it? Nobody trying to run it?
I'm opening MATLAB and stuff, so getting
Okay. What? Are you good? Is this working? Almost able to run it? You read all those files? Capital FFT?
Yeah.
No, it's in your folder on Canvas.
Yeah. I have my files.
You shouldn't have capital FFT. So yeah, it just needs to be in the same folder. Anybody run this?
Did you say we're not supposed to use capital FFT?
No, you are. If you use lowercase FFT, it's a different function. It'll just get an error.
Yeah, no.
So you're able to look at this data. So now kind of like investigate. Change the data you're looking at, change the cutoff frequency, like really mess around.
Yeah, capital FFT. You have FFT.net in your folder?
You should look at the different signals.
Oh, Pete.
So you should change the variable being
Oh.
filtered.
Yeah.
You should change the cutoff frequency. And you should develop an intuition for how when you change the cutoff frequency, it changes the way the signals look and their frequency content in the frequency domain. Do you want to run it? Okay. Signal processing toolbox? Okay.
Where is FFT?
It's on Canvas.
Like from today's lecture?
Yeah.
Yeah, I have all the files in the folder.
Do you have FFT? Can you refresh that?
Yeah, FFT didn't show up the first time I went in the folder.
That's because I
There it
didn't
is.
realize, I didn't realize I didn't put it in there. I noticed it like right when I was starting this demo and I dropped it in there. So yeah, if you don't see it, just refresh. You should be able to run it, adjust cutoff frequency, look at different signals, play with the data, have fun, become a filter expert. Anybody open up the program blow_filt? Do you want to try an experiment? You guys want to try something? Or are you still, like, do you still have stuff to do with investigating and playing around? Or do you want me to tell you something to do that's kind of neat? Let's do the thing that's kind of neat. Go open up the low_filt function. I'll do it with you. Open up low_filt. I want you to change the function name to high_filt and save as. So you're going to create a second function. So high_filt. And then here, instead of low, instead of low, you're just going to put high. Okay. And then save it. And then go back to your filtering function and plot, like create a high pass version of those signals and look at that. So I'll go back. I already have my filt. Anybody do the high pass filtering? Does it look like that? I just high passed it at the same cutoff frequency as the low pass. So just if you high pass something, it's just going to look like the ultra high frequency parts. So it's going to be very, very sharp looking. What's another thing that it's going to do? Has anybody used an oscilloscope in AC coupling? What else? Like, how could you immediately know if the signal had a high pass filter on it? Like looking at its data. Has to do with something that you mentioned earlier. You're recording a signal. You want to know if it's high pass filtered. How can you find that out? What will a high pass? Does a high pass filter have 0 hertz? No. Right? If it's high pass, it means it's cutting off the low frequencies, which means 0 is gone. So if it doesn't have 0 hertz, what does that mean that it has? It has a 0 mean. So now imagine you have your signal. You give it a signal of 10, it's going to immediately drive that signal back to 0. So a high pass filter, well, you can tell something's high passed if it's always trying to go back to zero. And the speed at which it goes back to zero is the cutoff, has to do with the cutoff frequency of that filter. So if you've ever used a filter with the AC coupling, you would notice it's always trying to go back to zero. That's a high pass filter. You guys have you guys gotten some experience filtering data, looking at it, looking at frequency content, kind of building that intuition? Yes or no? Yep, you feel good about that? Okay, let's keep going. We only have a couple more things. We might even end a few minutes early. Okay. So let's talk about how you would choose the cutoff frequency for a filter. So let's say now you have these tools, you know how to filter things, and you suspect you might need to filter something, but then you think, what do I set that cutoff frequency value to be? And how do I know that it's set correctly? And this is the answer. It's set by the engineer, so we can set it to be whatever we want. So that makes it easy. But the main goal is we want our filter to remove artifact or noise, but not remove signal. And there's no like right answer to that unless you have usually you don't have a super clear picture of what is your signal and what is your noise. You can usually have some idea based on, I know my signal is going to have this kind of frequency. I know there's a heel contact event that's going to create a sharp high frequency noise. But as the engineer, we kind of choose what the cutoff frequency is to protect the signal, and we get information about the signal's frequency content by looking at it in the frequency domain. So what you were just doing. Make sense? Okay. Now let's talk about like how this might occur in software. So this is, I think, potentially my last slide or close to it. This is the way it's commonly implemented. So I'm going to show how we implement it in MATLAB, and then next lecture we're going to do it in Python. It's going to be very similar. So this is this function, the filter that we were just talking about. It only has a couple of things that matter, but these are the key concepts of filtering. So this function, filter data, it's going to output its filtered data. We call it low filter, and then it has a number of inputs. And these are the common inputs for filtering functions. The first input, in this case, is the sample rate. So these filters need to know how fast the data are being sampled. The next input is the order, which we'll talk about in a second, the filter order, so that's capital N. The next input is the cutoff frequency. And the final input is your data. That's typically the information that you provide. Let's talk about two things. First, butter. What is butter? Why does that say butter? And then, so what's butter?
Is that the name of someone who made something?
It is. Butterworth. Yeah, it's a Butterworth filter. A Butterworth filter came from a guy named Butterworth, and it's a specific shape of the way frequencies get attenuated across frequency. So it's a Butterworth is a specific shape of a filter. So when I say a specific shape of a filter, does that make sense to you? Who thinks they're tracking that? Shape of a filter. Okay, cool, good. So a Butterworth is probably the most common shape of a filter. Anybody else? Anybody know any other shapes of filters? Any other common names? Chevy would be another one named after somebody. Or boxcar, that's another one. Okay. The way that these libraries typically calculate or receive their frequency, their cutoff frequency, is in typically this way. So what this is doing, you might tell what that's doing. So what it's actually doing is taking our cutoff frequency and dividing it by the half of our sample rate. What is that doing?
Something related to Nyquist.
Yeah. So lots of these libraries receive the cutoff frequency in a normalized fashion, where it's represented as a fraction of the Nyquist frequency. And that's just to make this like generalizable, because this library is used with things that are recorded at all types of frequencies. So this is how they set it up, and it's common. It's a good way to do it, I think. So this this is, I would say, this is an API for MATLAB's filter function, which is just butter and then filter. So I made this API and I did the convenience of kind of not having it be entered in this normalized way, so it calculates that for you. Does that make sense? Like what's going on here? Anybody know what B and A are? Just getting into stuff we're not really going to learn. They're the filter coefficients. So what this filter is, the way that like data are actually obtained when using a filter is through a product of samples, so your actual data backwards in time with these coefficients. So those coefficients become how the data are actually calculated, but you don't really even know what they are. Just know that they're filter coefficients, that's a thing. And then this is like a lot of filtering libraries kind of use this format where they have a function that will create the filter coefficients for you, and they have a filtering function that will use those coefficients to filter. I have a really hard question. I would be surprised but excited if somebody got it. So this function filter is the same function of another MATLAB function that you've used a ton in class. Anybody know what it is? Like it's called something different, but it's the same concept, same exact math. LSIM. We talked about LSIM. That's how we created our like forward simulations in time. We used a MATLAB function LSIM, which is creating something in time. That's filter is doing the same thing. Okay. So I just want to fill this out. This needs sample rate, filter order, cutoff frequency, and data. Okay, quickly we'll talk about N. What N is doing is it's controlling how steep this is. The filter order, so this is like back to our kind of definition of multiplying signals. We have our red function we're multiplying in the frequency domain, and the order is going to make this transition of the filter be steeper or less steep. What will that do? Anybody know? What if we filter more steeply? Or with a quicker transition? Yeah.
You're gonna let less frequencies after your cutoff point like pass through.
That's right. And so that would be, I'd say, like a heavier filter. Like we're filtering it. We have a high order that's going to make it be very steep, and that will make it have even less of those other frequencies beyond the cutoff frequency in your signal. The only reason we wouldn't want to just increase the order a ton is because it adds computational complexity. I usually use third order filters, which is like, I think, a good balance. Does everybody track like what this is showing and what the transition is, order, how all that relates? You guys are with me on this? Okay, good. All right, last slide. I want to kind of begin also by telling you a very, very common filter. This is about how we would implement it in software. So we're going to learn LowFilt is your API to use MATLAB filtering, and we're going to get a Python-based API to do the next lecture to just quickly re-go over it in Python so you know how to do that. And then this is just a last slide on implementing it in software and an easy way to do it. I want to make sure you guys know that filtering can be done both offline and online. So it's a little different. It isn't exactly the syntax that you would write, but it's the same exact thing. What's the difference between filtering offline and online? It's the first one. Yeah.
doing something, and offline it's like you have all your data points already and then you filter.
Yeah, so offline is what you just did with the data that I just gave you via Canvas. That's all offline analysis. The data's already been collected. You're just processing it and looking at it. Online is you're controlling your ballbot in the loop. So online, you're filtering. You need it to be used right then, and you don't have knowledge of the future. So it adds like a little bit of an extra set of constraints around solving the filtering. So that's online versus offline. And this class, offline will be stuff like homework. Online will be stuff like ballbot control. So you might want to filter online. There's going to be sort of a different way to do that. In real time, filtering can be done with a short set of products and sums. We will use Python and MATLAB API, so you won't have to actually do any of that. You will not have to implement yourself, which is common. Like now we just use libraries for this kind of thing. We don't really have to write these from scratch anymore. Filters cleverly use the previous values to construct the filtered output, so they're efficient in about storing values and retaining them. This has to do with how the coefficients are used. So now let's think about a moving average filter, which is a type of low-pass filter. I'm going to just tell you how we would construct this. So this requires no API. This is just one line of code. So a moving average filter is going to store, a length of data trailing in a buffer. So it's going to have something like 2 to 5 most recent points, and then it's going to create your output of your data x of k. It's just going to be the last nk point or nf points that you've saved in your buffer multiplied by 1 over nf. So it's just a moving average. You're going to take all your data, slide every time that you loop. You're going to increment 1. You're going to just let this moving average filter your data. This is a low-pass filter. It has a different shape. So it doesn't look like a Butterworth. It looks like something a little bit different, but it's going to be, for all intents and purposes, very similar. It's a low-pass filter. You don't really, unless you're really maybe a signal processing expert, you probably wouldn't need to care a ton about the specific shape of the filter that you're implementing. It's more, what is its cutoff frequency, and what is it, high pass, low pass, or band pass? Okay, so do you guys track the moving average filter? Could someone come up and draw the function, the multiplying function for me? Or just tell me how to do it? What's the multiplying function look like? No, that's too hard. What's the multiplying function in the time domain? It just looks like this, yeah? So if this is time, it's just going to take all of your values, multiply them by this, and then create the sum. What if these coefficients weren't all the same? So as it's written, they're all the same. That's the moving average. What if they weren't all the same? What would that do? Yeah.
It would bias it towards some specific value.
So it would bias it towards something, towards a specific value, or
And then a position. Like if you have the coefficient term of the point that you was collected 2 points behind, then we would bias towards that point if that coefficient was greater.
Okay, so I'm going to say that a little bit differently. I think that's right. I'm going to say it would bias it in time, which would be so now we can wait. We can begin to wait, where in time we want the emphasis to be, and then each one of these values is the previous x of k, correct? So every value was at one point in time, the x of k being calculated by this filter. So all of these values of x of k have all of their past values in them. This is what I was saying about kind of cleverly reuses previous values. So through this concept of shaping these values, we can actually get really good control over the frequency content that's allowed through. So these coefficients that end up at the beginning of these kind of multiplications and sums in the time domain, those end up related to those coefficients B and A. Yeah.
Just as a guess, this like the frequency domain function look kind of like an inverse function.
What would the frequency response look like for a moving average filter? Something like this. Something like that, or down and then. This is all I have for today. So we have 8 minutes. I want you guys to be able to come up and get your exams unless you guys haven't done that. And you guys could get shirts if you haven't done that. And then if there's anything about filtering, now's a great time to ask. There's going to be questions on it on a homework that's going to go up today. Any thoughts on filtering? How do you do something? Next lecture is Python. All right. Have a great Thanksgiving. Come to office hours if you want.